Hello and welcome to the video demonstration of our advanced encryption standard symmetric key algorithm written in C++. This code was made by me, Jeremiah Webb, and my partner, Sarah Gleixner. So right now we're just looking at the GitHub repository page, and to begin, we're just going to copy and paste it. There we go, it's cloned. Great, so we have the program, we have everything here, and it actually tells us in the README how to compile. Perfect. And for command line usage, so if a user wants to input their own keys and such, we have to run this command, just copy it. Great. You can see that we have base test cases that we've ran just to show that the program is working and actually functioning. So for this case, we're just going to try 128-bit ECB encryption. So I have some pre-selected keys and plain text to use for our test. One, and you can see that it's asking the user, okay, what do you actually want to do? We're going to encrypt, and we're going to use ECB mode. So you can see it's asking enter the secret key in hex. Enter the plain text in hex. Perfect. You can see that it actually outputs the encrypted text. And so let's say, for example, we want to decrypt it. We just run it again. 120-bit. Let's decrypt it this time. ECB mode again. Going to reuse that same key. But this time we're going to take the encrypted hex. There we go. You can actually see it's the exact same string. 5477, and then up here, 5477. Perfect. We can even test, let's say, CFB, because that one actually requires an IV. So let's encrypt this time. CFB. It's asking for the key again. There we go. Reminder that has to always be in hex. Additionally, this library, as you can see in GitHub, plain text must be divisible by 16. I have not implemented, or excuse me, we haven't implemented padding, as that is not required by NIST in the AES-NIST publication. I have the links below in the GitHub. Let's put in the plain text, and you can see it's asking for an IV this time. I have a pre-selected IV. Perfect, we got our encrypted hex. Let's see if we can actually decrypt it and get the same thing back. We're going to decrypt this time. Well, this time we just did CFB. Enter the secret key. Enter our plain or our ciphertext. There we go. It's going to ask for the same IV. And there you go. We actually got our text back. 5477, 776F. It's right up there. So that's essentially just the demo, just showing that it can work, that it can actually encrypt, that it can decrypt. Um, and to keep our time short, I'm not going to go through all 128, 192, 256. If you do want to do that, it's the same thing, essentially, just going through to decrypt, which mode, and then just inputting over and over and over. Without further ado, let's get into the main kind of code part. So first we're going to look at the AES.H. Let me scroll to the top. Here we go. So essentially what AES.H does, it provides an interface for the user to actually use the library in code. So we can see that, okay, we have an enumerated class which allows the user to define exactly what length we're going to use, the class of just AES. These are all the built-in private functions, and then these are the public functions that essentially what the user can actually call. So this is the constructor, this is the actual encryption methods, and you can actually see that you can use a char array, an unsigned char array, or you can use, if it's more convenient for you, vector unsigned char arrays for your, your plain text, your key, your IV, and then some utility functions. Below all of that is we have definitions of like the S box, the inverse S box, the Galois field multiplication tables, and then the CMDS matrices. Next, we're going to go into the meat and bones of the actual program, the AES implementation. You can see that this is the constructor. Essentially, these are the public functions that the user can call. As you can see that, yes, you can input. You have to input the length of the actual plain text, but you can use unsigned char arrays for both your plain text and keys. Without getting into much into the nitty gritty, we can see on a big portion of it is shifting and the substitution of the bytes. We can see that a state is used, a state array, a multi-dimensional state array is used for the substitution of bytes. That's where the actual, bytes are actually held while they're being encrypted. You can see that we have round key functions, the mixed column functionality, rotation of the words, substitution. This is the key expansion algorithm. This was a joy to write. So essentially, what we used was the AES NIST documentation to go off of. Um, the documentation actually goes in exactly what you need to do. It just gives you, for example, let's see the add round key transformation. It tells you exactly what you need to write, and actually gives you pseudocode. So, and then inverse subbytes, inverse mixed columns. This is all for decrypting, XORing blocks. These are just XORing the actually entire um, states. The utility functions, and then these are more public facing functions that the user can call to begin their encryption. So let's actually see this in practice. We're going to go into the main.cpp file, and we're going to begin at main. First, we can see that running test cases is a void function, which just shows the user previously, as we can see, these are what's run to begin. And as you can see, you just need some unsigned char vector arrays, and to actually create the AES object to begin encrypting, all you have to do is AES, you can name it whatever you want, define the key length. This is just an enumeration value that defines, again, I can show you in the constructor, how many rounds we need and how many keys we need, round keys we need. This just essentially just checks, okay, what we need to, if it's right or not. But for the user input, we actually have a struct to user test to essentially hold all of the user's data. So in theory, the user can actually use the struct for their own test cases or just for general encrypting and decrypting. This is how the user actually can input. If the args are greater than 1, it's going to ask the user, okay, what do you actually want to do for bits? How many bits do you want to do? This runs specific case use or specific case functions, excuse me. And as we can see, this is how this function's great because essentially when inputting a string, the string isn't inherently hexadecimal value, and this is how you actually convert that like that ASCII string into a hexadecimal value, because a in ASCII does not equal a in hexadecimal. Okay. Again, this is another creating user tests. So again, this is just essentially the menu, just asking, okay, what do you want to do? What set, like essentially a setter function. And then we get into the meat and bones of the actual user test encryption and decryption. The user has to ask, okay, well, what do I want to do? Let's say I want to decrypt my already encrypted text. Well, it's going to it's going to, might ask for an IV here. Uh, and again, the user choice actually refers back up to here. It's going to ask, do you want to do CFB, ECB, CBC, for example? Um, right here is a CFB decryption case. Um, as you can see, it's relatively simple. This is just essentially inserting all the data and getting all the data from that, again, user test struct. But overall, you can see that, and this is just the encryption, but overall, you can see that the AES implementation does actually work. It's located on the GitHub. Excuse me. Legion 173 at AES-ERAU. Thank you.